So we're going to continue with covalent bonding, and we're actually going to have a look at the shapes of covalent molecules and what shapes they form. So we're going to use VSEPR theory, or valence shell electron pair repulsion theory, to figure out how these shapes of molecules are actually formed. So the first one we're going to look at is beryllium chloride. So beryllium chloride is BeCl2. Now, beryllium on the periodic table is number 4 and chlorine is 17, but we're only interested in the outer electrons that are involved in bonding. So in beryllium, the first shell is 2 electrons, so this is in group 2, so it's got 2 electrons in the outer shell. Chlorine is in group 7, so it's got 7 electrons in the outer shell available for bonding. So the way this sets itself up is you have beryllium, and again we're only interested in the outer ones. We got 1, 2 electrons, and then we have chlorine bonding. But what happens with these 2 electrons is the 2 electrons orientate themselves so that it shares with the chlorine. So we'll put an electron for beryllium here and here, and then what we're going to do is we're going to put in the chlorines. So we'll put in chlorine here, which is a much bigger atom, but you get the picture. So we've got one there. So chlorine has got 7 electrons in its outer shell. So we're going to have 1, 2, 3, 4, 5, 6, and then 1 in here, and then the same on the other side. We've got 1, 2, 3, 4, 5, 6, and then 7, which is there. So now let's look at what we have. We have beryllium, and we've got a pair of electrons here shared, which gives us our single bond. We have another pair of electrons here shared, which gives us another single bond, and we've got chlorine on either side. Now some students would say, well, can the shape be something like this? And the answer is no. And the reason why is because if you think about it, in magnetism, similar charges, the same charges, will repel each other. So electrons will repel each other. So when you actually get to this stage, the electrons in chlorine and the electrons in chlorine here are going to repel each other, and they're going to push each other up. The chlorine will push as far as here, the chlorine will push as far as here, and they won't go any further because then they'll be pushed back down again. So that's why you end up with this straight line. Now, when you have a shape of a molecule like this, this is what we call a linear molecule. So this here is linear. This has a bond angle of 180 degrees. It's a straight line. So it's linear. It has 2 bond pairs. So there is 2 pairs involved in bonding. And something to add in here, there is 0 lone pairs. That comes into play in the next while with some more molecules. So now what we're going to do is have a look at the next shape. So the next shape we're going to have a quick look at is 3, which is, let's say, we'll try boron trichloride. So BCl3. And boron has got 5 electrons. Chlorine, as we've seen already, has got 17 electrons. Boron is in group 3. So it's got 3 electrons in the outer shell available for bonding. The first 2 are obviously in the first shell. And then again, group 7, we've got 7 electrons. So again, we're going to draw exactly the same thing. But how do we draw 3 chlorines around the boron? So the way this sets itself up is we have boron in the center. And again, on the outer shell of boron, we've got 3 electrons involved in bonding. The 2, we're leaving out the first shell. The way that these arrange themselves so that they are the furthest region apart is like this. So boron sets its 3 electrons up like this, and then chlorine joins on. So we've got chlorine there, and chlorine here. So there's your chlorines. Chlorine, of course, is 1, 2, 3, 4, 5, 6, and then 7 there. And we've got 1, 2, 3, 4, 5, 6, 7, and then we've got 7 on the other side. 2, 4, 6, and then we've got the 7 in there. So as you can see from here, we now have 3 bond pairs. So we've got a bond pair there, a sharing pair of electrons, a sharing pair of electrons, and a sharing pair of electrons. So that is 3 single bonds. And this is the way that this sets itself up. We have boron with a chlorine, and a chlorine, and a chlorine. And this is the most efficient way that it can push themselves away from each other. Again, the electrons will repel from each other, giving this shape. This has got an angle of 120 degrees, so a lot less than your linear one. And this shape is trigonal planar. So it's trigonal because it's in a triangle shape. It's planar because it's in the plane, it's not in 2 dimensions. So on this one, this has 3 bond pairs. And it has 0 lone pairs. So anything that obeys this, any molecule that you can find that has 3 bond pairs and 0 lone pairs, it will be called trigonal planar. So that's the second one. Let's move on to the third one. So in the third one, we're going to have a look at CH4. So again, with CH4, just like these other ones, we're going to have a look at its general shape, how many electrons it has. Carbon has got 6 electrons, hydrogen has got 1 electron. Of course, carbon is in group 4, so it's got 4 electrons in the outer shell. Hydrogen is generally in group 1, so that's got 1 electron in the outer shell. So carbon, we draw it like this on a Bohr diagram. So we've got 1, 2, 3, and 4 evenly spaced out. And then our hydrogens join on. So there's 1 hydrogen, 2 hydrogens, 3 hydrogens, and then there's our 4th hydrogens. All electrons used up, so again, no lone pairs, nothing left out here. And your hydrogens have got their electrons too. So when you're drawing this, this is going to form this shape. So the shape that we draw for methane, generally we draw it like this. And that's not actually the shape, and we're going to have a look at that now. We draw it like that because we often draw methane, and it's easier to draw it in 2 dimensions on a board or on a piece of paper than it is to actually draw it the way it sets up. So in this particular one, it's actually what's called a tetrahedron, or a tetrahedral shape. And this is the geometry. So the way this actually sets itself up is you have a hydrogen going up to the top, you have another hydrogen to the side here, and then we draw a wedge shape to indicate a hydrogen coming out to the front. So it's in 3 dimensions now. And then we draw a lined wedge shape going out at the back, which indicates that the hydrogen is going out at the back. These angles, all angles, are 109.5 degrees. So it's important not to draw this hydrogen here at 90 degrees. It's 109. And again, that would be 109 degrees, and that is 109 degrees. They're all the same bond angle. So this is tetrahedral, 109.5 degrees. And in this one, we have got 4 bond pairs. So we have 1, 2, 3, 4 bonds, 4 bond pairs, and 0 lone pairs. We've got, again, in this one, we have no lone pairs. 0 lone pairs. The next one then that we're going to have a look at is ammonia, NH3. So NH3 is next, ammonia. And let's have a look at what we have here. We've got nitrogen, which is 7. So this is in group 5 of the periodic table. We've got again hydrogen, which is 1 electron, and this is in group 1. It's 1 electron in the outer shell. So when we're drawing NH3 ammonia, same thing, we start with nitrogen. We're not interested in the first 2 electrons, we're only interested in the outer 3. Now, when we draw these outer 3 electrons, this is the way it sets itself up. So if you look, we have NH3. Up above, we had BCl3, which looks like a similar molecule. You know, you have 1 atom bonded to 3 atoms. So you would imagine that looking at BCl3, I can find it here, that it is going to form trigonal planar, 120 degrees. That's what you'd be thinking. But that's not actually what happens in ammonia. So in ammonia, you don't get Cl3 here, or Cl and a Cl, and then this formation and 120 degrees. Okay, you don't get that, and there's a reason why you don't get that. So when we're drawing this out, we have to bear in mind the fact that nitrogen has got we have got 5 electrons to fill in on the outer shell, and we only have 3 hydrogens that are bonding to it. So what we end up with is 3 hydrogens surrounding this. So we get a hydrogen here, we get a hydrogen here, and we get another hydrogen here. And each of those hydrogens brings an electron. But nitrogen has got 5 electrons to fill. We have 1, 2, 3, and we have 4, 5. These 2 electrons here are not involved in bonding, so this is what's called a lone pair, because they're on their own, they're a pair, they're not bonded to anything. And this is how this is different in BCl3. In BCl3, you had no lone pairs. All the electrons in boron were used up, but in ammonia, in NH3, they're not all used up. Because of this, this lone pair exerts a repulsive action on the hydrogens. So it means that the shape of the structure is going to change. The shape of this structure looks like this. We've got N, and we have a H on one side. We draw a wedge shape coming out at the front. There's another hydrogen coming out at the front, and then we have a H at the back. And we also indicate the fact that we have a lone pair by putting our 2 dots up above. So this particular shape is what's called pyramidal. Or trigonal pyramidal. There's a couple of names on it. So pyramidal is what we have. This has got 3 bond pairs, which is the same as previous one, boron trichloride, but this has 1 lone pair. And because of that 1 lone pair, it pushes the hydrogens down and changes the shape of the molecule. So the angles in this one here is 107 degrees. So again, it's less again. So that's the difference between them. They are not the same. Finally, the last one that we're going to have a look at is water, which is H2O. And again, in this one, oxygen is 8 and water is 1. So oxygen has got 6 electrons to fill in, hydrogen has got 1 electron to fill in. So in this particular one, water is going to set itself up like this. I won't draw the board diagram for this, but here's the shape. Now, some students will always ask, why does water not look like this? Why is it not 180 degrees? Well, the reason for that is in oxygen you've got 6 electrons to fill in. So there's 1, there's 2 that are involved in bonding. Then there's 3, 4, 5, 6. So there's all the electrons in the outer shell of oxygen. But again, only 2 are involved in bonding. So what you have is you have 2 lone pairs. And these 2 lone pairs push the bond with hydrogen down. So you end up with what's called V-shaped. And I've drawn it upside down. But drawing water like this as well is perfectly acceptable. So that gives you your V-shape. These particular angles here are at 104.5 degrees. It's V-shaped. It's got 2 bond pairs. The 2 bond pairs are here and here. And then you also have 2 lone pairs. And anything that obeys that rule, 2 bond pairs, 2 lone pairs, is going to be V-shaped.